Okay, what I'd like to do over the next 20 minutes or so is discuss some of the structural rearrangements which occur during the CO oxidation reaction over platinum rhodium. What I'll start by doing is talking about some of the CO-induced effects for the rhodium component. I'll then describe a unique feature for the platinum component, and then by combining these, hopefully gain some information about the mixed bimetallic catalyst system. See, we've already got the first slide, so I'll start there. Well, the effect of heating in CO on the rhodium, on exported rhodium catalyst is fairly well known. That is, if we start with a catalyst in a high dispersion, then essentially CO is dissolved in the bridged mode and in the gem dicarbonate on two bands here. If we then heat this in CO, this is heating at 10 degrees per minute, then we reach a temperature, in this case at 508 K. Can I have the next slide, please? Okay. So between about 508 K and 523 K, there is a dramatic reduction in the intensities of the gem dicarbonyl species, a growth of a new band due to linear carbonyl, and then if we take this up to 573 K, which was the temperature of the original hydrogen reduction, then we're left essentially with only a linear carbonyl species. And we can show that the loss of gem dicarbonyl isn't a desorption phenomenon by then cooling back down in CO, and note there is no redevelopment of the gem dicarbonyl species. So essentially we're looking at an irreversible process. Can I have the next slide, please? Now, if we carry out this process in a flow of nitrogen containing CO and oxygen, in which CO is in excess, then essentially the same features will be observed. But because now the temperature at which will dominate the control of the system will be the temperature at which complete conversion of oxygen takes place, there is now significant desorption of the gem dicarbonyl species, and therefore heating in CO oxygen, in which CO is in excess, will be less effective in agglomerating the dicarbonyl species into a crystalline. If we then move on and look at the system where oxygen is in excess, basically still not the gem dicarbonyl species, we then go into the temperature range in which we're getting complete conversion of CO, and then there's a dramatic reduction in intensity of the gem dicarbonyl species. Now we can show that this is not due to agglomeration, formation of a linear carbonyl plus reaction, by then switching the oxygen supply off, and you can see that in contrast to the second slide I've shown, there is a rapid regeneration of the dicarbonyl species, and then if you leave this as a function of time at 573 in CO nitrogen, then we can then begin to produce the linear carbonyl. And if I leave these for a further length of time, then essentially we just eliminate the dicarbonyl species and we end up with just a linear carbonyl. Now, I said that during this process what we're mainly looking at is a straight desorption into the gas phase. However, if you can see, I don't know how clear this is from the back, maybe I should have plotted this on another scale, but there is a development of some weak feature here, which is common to all spectra heated in where we're looking at CO-oxygen mixtures and in excess of CO. So there is some sort of structural modification resulting in this weak band at 1905 wave numbers. Now we can show how this affects the catalytic reaction, this agglomeration in CO, by carrying out a runoff in temperature in a CO-oxygen mixture, heating for a brief period in CO alone at 573 K, and then cooling back down and repeating the runoff. Can I have the next slide, please? and this is shown here. So this is the initial run up here, and you can see that this is exhibiting a much less steep light-off than the re-reduced sample, and in addition, as we approach as a CO conversion against temperature here, as we approach 100% conversion, then we get this sort of double maximum shape curve, which is something which is also seen in the case of rhodium 100, for example, whereas you move to something like a much more close packed crystal phase, such as rhodium 111, then this gives a similar type of light-off behaviour, rate temperature maximum, which we see here. So essentially, there is some modification to the rhodium crystalline surface. And can I get the next slide? And I can represent this as some. So we look at the white dots here, which represent the gem dicarbonyl sites, and then we have these small crystallites, which initially rhodium CO is absorbed in the bridge mode. So we have loosely packed rhodium crystallines, which we saw both in the form of the twin peak maxima and due to the fact that CO is absorbed in the bridging mode. If we then heat this in CO, this is below the original hydrogen reduction temperature, in either neat CO or where we have CO in excess, then we form we increase the particle size to some extent, but now we have a much closer packed crystal face, as shown by the fact that we no longer have this twin peak maxima in the rate temperature plots, and also that the dominant mode of absorption of CO is now in the linear mode. However, when we carry out this in an excess of CO, then the dicarbonyl species can no longer agglomerate into what's the original particle, possibly as a result of oxygen absorbed at the peripheral atoms. However, where there is an agglomeration or a cluster of dicarbonyl species within close enough proximity, these sites come together to form these small crystallites, which I showed, which resulted in the small band we see about 1905 wave numbers. Can I have the next slide? Now when we move on, can I shift this towards me? That's okay. So this is the spectrum now. We're looking at platinum, rhodium over aluminum. Now just ignore most of the spectral features, and we just concentrate at the moment on the gem dicarbonyl species. Again, so this is heating in a 4:1 oxygen-CO mixture, so again oxygen in excess. Again we reach a temperature equivalent to about 100% CO conversion. There's a dramatic loss in intensity of the gem dicarbonyl bands, but again, if we switch the oxygen off, then these species are readily formed again, showing that we're basically just looking at a desorption of CO from these sites. And as a function of time, at 300 degrees Celsius, heating in CO, these dicarbonyl sites are eventually eliminated from the spectrum, and we end up with just the linear carbonyl species. And again, as I showed in the case of rhodium alone, we see the band beginning to grow up here in 1905 with these small rhodium clusters which are just on the surface. Now we can do the same sort of things I showed earlier by ramping the temperature up, agglomerating in CO, and then cooling down in nitrogen and repeating the run-up to compare the light-off temperature or 50% CO conversion temperature for a series of catalysts. Can I have the next slide? So here's what I have is the 50% CO conversion for the monometallic catalysts, and then 2 platinum rhodium catalysts. This one is prepared by sequential impregnation sequence, and then this is prepared by a co-impregnation. And in this case I've chosen a reaction mixture at 16:1 oxygen to CO, in which case the fresh catalysts here for the platinum rhodium and the platinum catalyst alone exhibit equivalent light-off temperatures. And basically what you can see if you look at the samples which will be heated in CO at high temperature. That essentially it's only the rhodium-containing catalyst, so this is neat rhodium and the platinum rhodium catalyst, so it's only the rhodium-containing catalysts which are improved in light-off behaviour following this high-temperature treatment in CO alone. And platinum is essentially only looking at about 12 degrees reduction in light-off temperature. Now, despite the fact that platinum doesn't exhibit improved light-off behaviour, there is some sort of change in the particle surface following these treatments, as we can see if you look at the infrared spectra. Can I get the next slide? Showing here. I don't know if anyone can see this. No. I'll continue and describe anyway, and I won't say as you can see clearly. Well, as you can see very clearly, these are a series of spectra increasing temperatures for a fresh catalyst, comparing these with samples which will be reduced after reaction in CO and then go back down in nitrogen. In the case of fresh catalyst, the linear carbonyl band is clearly composed of three features. So we have asymmetry at higher and lower wave numbers, and you see the high wave, maybe you don't see, the high wave number component becomes resolved as we move to higher temperatures. So we have a very heterogeneous surface. Whereas in the case of the fresh catalyst, the reduced sample rather, then we only see this very narrow sharp band due to the linear carbonyl species. So we've now got a much less heterogeneous particle surface. Can I maybe swing this over a bit? Now, what I've done here now is to plot the band maximum as a function of temperature. So we have temperature across the bottom here, and then the frequency. And as you can see, if we start off, this is a fresh sample here, there's an initial decrease in frequency, then we reach a temperature at which, over the next short period, or a short increase in temperature, there is invariance in the carbonyl stretching frequency. And this occurs for a fresh catalyst sample, irrelevant of the oxygen CO concentration, as long as oxygen is in excess, and this occurs about 2064 plus or minus 1 wave number. However, in the case of the reduced catalyst sample, well, the first thing is that we're now monitoring a band which probably relates to the high frequency component here. So the frequency is much higher initially, but the other important thing is we now see invariance at about 2076 wave numbers. And this period of invariance in the carbonyl stretching frequency occurs over a much wider temperature range. Can I have the next slide? So, what I've done here, I don't know if you can see these values, but it's not really important. We have 1% CO, and then I'm increasing the concentration of oxygen in the flow. And then basically looking at the 50% conversion. And as we might expect, there's as we increase the oxygen concentration, there's a gradual decrease in the light-off temperature. However, probably more important is if we then take the 80% conversion temperatures and compare these with the temperature at which the onset of the carbonyl stretching frequency becomes invariant, then we see some degree of correlation. And I tried to plot this in this here. So here we see the onset temperature for invariance in the carbonyl stretching frequency, the temperature for 80% conversion, and well, at least there's some degree of correlation. Maybe it's not the best correlation ever seen by mankind, but when you take into account that we're looking at an equivalence ratio change from about 2 up to 70, then maybe it's not so bad. So we can now use this information gained about CO oxidation over platinum to look at the distribution of the two metal components within the bimetallic system. Can I have the next slide, please? So basically, well, if we just ignore, first of all, the two lower curves here, as I said earlier, We only see invariance where there is an excess of oxygen in the flow. So these are for stoichiometry and in a CO excess. But again, in the case of platinum, this is 1% CO, 1% oxygen. We see a short period of invariance in the carbonyl stretching frequency, about 2063 wave numbers. And when you compare this with the behaviour of the platinum-rhodium catalyst produced by the two impregnation sequences, then in both cases we also see the short period of invariance. Now, since this doesn't occur in the case of rhodium alumina, this would suggest that what we have in the case of both bimetallic catalysts is that there are either particles containing platinum only, or that at least within the bimetallic particles we have ensembles of platinum which are large enough to support this behaviour. Now we move on and go back to the samples in which we treated at high temperature in CO and compare these with the fresh samples, then we can get some information on how the two metals are combined within the catalyst. Can I have the next slide? Okay, so we look first of all at the catalyst prepared by the stepwise, the sequential impregnations sequence. And we see in the case of the fresh catalyst, again we see invariance in the carbonyl stretching frequency, again 2064 wave numbers, indicating that we've essentially got something that's very similar to the platinum catalyst on its own. And as we saw for platinum, if we then re-reduce this in CO, then again we see a shift to higher frequencies during invariance, but we still have invariance in the stretching frequency of the carbonyl. So we still have either platinum-only particles, or at least sufficiently large ensembles of platinum within the platinum-rhodium crystallites. However, if we move to the simultaneous impregnated catalyst, then in the case of the fresh catalyst, there is a brief period in which invariance in the stretching frequency occurs. Then when we go to the sample which has been reduced in CO, then essentially we just see a monotonical decrease in stretching frequency, and there's no indication of invariance here at all. And in this case we now have behaviour which is much more like the rhodium sample alone. So the surface has now become much more rhodium-like, but we're now carrying out reactions over a mixed CO oxygen additive. Now we can show how this incorporation of rhodium comes about, and we show the next slide. So first of all, we concentrate on this. Okay, this is the last slide. Okay, so first of all, what we are doing here is just frequency against temperature, and this is heating in CO. And so, as you expect for platinum itself, we just see a decrease in the stretching frequency. As we showed for rhodium, there is no linear carbonyl species until we get to the agglomeration temperature of 508 K. And then, as you produce a linear carbonyl, there's a much greater frequency and temperature dependence, so we have a steeper gradient in the curve here. What you might expect for a platinum-rhodium catalyst is that we see something which is like a combination of the two. So we drop to about the agglomeration temperature, and then the frequency should lie between the 2 points. And this is exactly what happens if you take a physical mixture of components, and this I've shown in the white spots here. We get to the agglomeration temperature, and then the frequency drops between the two. However, in the case of the platinum-rhodium catalyst, what happens is once we get to the agglomeration temperature, there is a massive switch, and we now have a carbonyl stretching frequency which is very, very rhodium-like. So can we just switch off this, and I'll conclude using the last transparency. So this is exactly what we had and how I explained the rhodium behaviour. But what I'm saying now is, in the case of the platinum-rhodium, it doesn't really matter if this is a rhodium particle, if it's a platinum particle, or if it's a platinum-rhodium particle. But if we heat under CO excess conditions, that's under a rich mixture, rhodium species will be incorporated into these particles. So within the car exhaust system, anytime we move to a rich feed stream, this provides one mechanism in which bimetallic particle formation may occur. Thanks very much for your attention.
You're showing that the light-off temperature is improved by this effect.
Yeah.
Now, I guess, and your last statement there is, I think, interesting, that light-off is a major problem in the automotive converter.
Yeah.
And so you're sort of saying that since you will be cooling in CO, to make this carbonyl.
I was cooling in nitrogen.
Well, but
I'm dipping in CO, yeah.
In the real world,
okay,
you're cooling in CO, and so you sort of, when your car is sitting there after it's been shut off,
that's right.
Making all this dicarbonyl, and that's a great light-off catalyst to start it up. I think that's an interesting observation as to what could happen in the real situation.
Perhaps I missed the point. What are actually the dots you show around it? So
these are the dicarbonyl sites. So these are the monotomically dispersed rhodium species.
So do you think they are atomically dispersed or some sort of small collage?
No, I think maybe originally before the absorption of CO they are small clusters, but after absorption of CO these will be monotomically dispersed.
So, then can you see at the beginning of the reactor? Can you see at the beginning of the reactor?
Not the first.
Okay, good point. But that's fine. So I think that this data here demonstrated that the behavior of the highly dispersed molecule is different from the common dispersed and the high one. So in this case, one that was found the difference from that room temperature and high temperature, the other relation to that.
I agree.
We have that question. A very marginal one, actually. I saw that you mentioned that you mentioned the intensity of CO2 gas.
Okay, yes.
I mean, do you think this really gas in the cell, or is it CO2 itself that has come?
No, this is CO within the cell.
Okay. Well, thank you very much.